can deduce several properties from our definition of the density matrix. First, the density matrix is Hermitian. Explicitly, we can write down a matrix element of the density matrix. We deduced we could write it like that. But of course, that's just equal to this. And that is just rho uv star. Because the density matrix is Hermitian, so also is the density operator, since the density matrix is just a representation of the density operator. Second, the diagonal elements, rho mm, give us the probabilities of finding the system in a specific one of the basis states, phi m. So, in the situation where these two indices are the same, for rho mm, then this product, of course, is just the modulus squared of Cm for state J. And that's the probability for a pure state J, that we will find the system in state M. Hence, adding these up with probabilities Pj gives us the overall probability of finding the system in state M in the mixed state. Incidentally, the off-diagonal elements, the ones in which the m's are not the same here, are a measure of what's called the coherence between different states, and we're going to come back to discuss this later on. Third, the sum of the diagonal elements of the density matrix is unity. That is, remembering that we can formally write the sum of the diagonal elements of some matrix or operator as the trace, using this notation here, of the matrix or operator. That is, formally the trace of a matrix or operator is just the sum of the diagonal elements. Then in this case, that means that we're looking at this sum here when we look at the diagonal elements, as we did previously. And that is just the sum over j of pj times the sum over m of all of these. And that is just pj added up for all of the different j's. And that has to be 1, because the state psi j is normalized, so therefore the sum of the squares of all of these coefficients has to be just 1, and the sum of all the probabilities pj of the various states psi j in the mixed state must be 1. Consider an operator A for some physical observable. Now we're going to be able to work out the ensemble average value from the density matrix. And specifically then, consider the product rho, the density matrix or operator, times A. So we can write that out. Here's rho times A. So here's our density operator or matrix, and here's A. We can therefore write some diagonal element of the resulting matrix as this expression. So here's our diagonal element. We take the same basis function on both sides, Hermitian adjoint here and the basis function over there. When we multiply that through, these are just numbers, of course, so we're left with psi q operating in all of these operators here and psi q on the other side. Well, this product here is just delta qu. And so we lose one of these summations here. We're just left with the sum over one of those indexes. And here's the expression that we have. Well, the sum of all of these diagonal elements then, so here is our expression for one diagonal element, is the sum over q of all of those, which we can write like this here. But that is just the sum over j of pj times this form here. These expressions here are simply the expansions of psi j in the adjoint and the original form. Note, this is the same as the ensemble average value of A. This thing here is just what we defined early on as the ensemble average value of the expectation value of A. Hence, we have a key result of density matrix theory. the ensemble average of the expectation value of A is just the trace of rho times the operator A. The density matrix can therefore be used to deduce any measurable ensemble average property of a mixed state. Hence, the density matrix gives us a full description of a mixed state. Note that this result is independent of the basis used to calculate the trace. The basis phi m could be any complete set for the system. Note also that if we have the system in a pure state, psi, in which case p equals 1 for that state, and is 0 for any other pure state, then we recover the usual result for the expectation value. That is, the trace of rho times A would just be psi A psi, which is the expectation value of A. So the density matrix description gives the correct answers for pure or mixed states, and sometimes we will see the density matrix used in a situation where we're only actually working with pure states. But we can use the density matrix formalism whether we're working with pure or mixed states, so it's a slightly more general way of writing down quantum mechanics.
So we've now found the first useful results from our proposal of the density matrix. First of all, it's a well-behaved mathematical object. It's a Hermitian operator. Second, the diagonal elements of the density matrix tell us the probability that we'll find the systems in any of our basis states if we choose to make an appropriate measurement. We have found that the sum of all of those probabilities is unity, of course. Finally, with our formula using the trace, we're able to calculate expected or ensemble average values correctly. This is true whether we're in a simple pure state or whether we're in a mixed state. So, as we said, we now believe this density matrix is as complete a description as we could have for representing our mixed state. It gives us the right answers statistically for any measurable property. We can't ask for any more than that from a representation of a state that is fundamentally a statistical distribution to start with. Next, we'll show how to describe how the system will evolve in time using the density matrix.